Our aim is to determine how altering the temperature of vinegar affects its rate on reaction with baking soda. I predict that if the temperature of the vinegar is increased to 40 degrees Celsius, then the rate of reaction will also increase. The independent variable for this experiment is the temperature of the vinegar. How will this be changed? 3 trials will be conducted for each set temperature, and we will have 6 set temperatures for the vinegar. A control, which is 23 degrees Celsius, 0 degrees Celsius, 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius and 40 degrees Celsius. The control will be 23 degrees Celsius, as that is the average room temperature. The reaction rate measured as time taken for the balloon to fill to 90 centimetres cubed with the chemical reaction producing carbon dioxide gas. This will be measured using a stopwatch in seconds. The time from when the reactants are exposed to each other until the point the carbon dioxide has produced enough from the reaction to inflate the balloon so it is standing upright without any collapsed edges. The control variables include 80 ml volume of vinegar to be used in each trial, 1 teaspoon of baking soda used in each trial, room air pressure of the experiment's environment, mercury thermometer used to indirectly measure the vinegar's temperature in each trial by measuring the surrounding water's temperature, baking soda temperature, the thickness and volume of the glass bottle. The same type of balloon will be used for all trials. The stopwatch used to measure the time taken for the balloon to inflate to a set point will also be the same. Materials required for our experiment include 2 litres of vinegar, 200 grams of baking soda, 300 ml a glass bottle, a plastic funnel, 1 litre medium-sized measuring bowl, a kettle, 2 litres of water, 500 grams of ice cubes, a mercury thermometer, 1 teaspoon measuring scoop, 80 ml measuring borer, a knife, a dry cloth, 18 30 centimetres balloons, a stopwatch, a pencil, a piece of paper, a calculator, a ruler, safety glasses, an apron. 80 millilitres of vinegar was poured into a glass bottle, which was then heated or cooled by placing it in the bowl of water, which also contained a thermometer. 1 teaspoon of baking soda is funneled into the deflated balloon and attached over the top of the bubble, prior to emptying the baking soda into the vinegar containing bottle, commencing the chemical reaction. Time taken from point of reactants coming in contact with each other to when the balloon is inflated just enough to stand upright with no creased folds is recorded. The time is recorded using pencil and paper, and different trials with varying vinegar temperatures are then conducted. I'll now run you through a control trial. Firstly, a medium measuring bowl was filled to a volume of 700 ml of room temperature water. A thermometer was then placed in the water to monitor the water's temperature and ensure that it was at 23 degrees Celsius. Our empty bottle was placed to rest upright in the bowl of water. The measuring cup was filled with 80 ml of vinegar. A plastic funnel was used to pour the 80 ml of vinegar from the measuring cup into the empty glass bottle. The funnel was then dried with a cloth. We've now waited 10 minutes, and this has ensured that the temperature of the water, the bottle, and most importantly the vinegar has reached thermal equilibrium, which also means the vinegar is 23 degrees, as is the room temperature water. One teaspoon of baking soda needs to be measured from a spoon. It's essential to level it out. Using the funnel, this needs to be placed into the balloon. You need to ensure that all air is squeezed out of the balloon. When attaching the balloon to the bottle, it's important to make sure that no bicarbonate soda reaches the vinegar, gets through to the vinegar. So it's essential to pinch the balloon near the bottle's mouth. Upon releasing my squeeze on the balloon, the bicarbonate soda will flow into the vinegar, starting the reaction. As I do this, I need to start the timer. As we can see, the reactants have reacted together to form carbon dioxide as a product, which has inflated the balloon. This was then timed using the stopwatch. Gas was observed to be produced and inflated the balloon. The time then needs to be recorded using pen and paper, pencil and paper. If we then repeat steps 3 to 15 a further 2 times, then we complete the set of control tests. We then repeat steps 3 to 16 for all the other set temperatures, i.e. 10 degrees Celsius, 20 degrees Celsius. To ensure that the vinegar is at that temperature, we either have to apply ice cubes to the water to cool it down, or boiling water from the kettle to heat it up to reach their temperature so it gets a thermal equilibrium. Upon doing all the tests, we then calculate the averages by dividing the sum of the 3 trials by 3. Before we started collecting results, we conducted some preliminary trials. Throughout these, several issues were identified. Firstly, it was initially planned to reuse a single balloon for every trial in the experiment. However, moisture, as water is a product from the reaction, the water vapour stayed inside the balloon. This moisture then prevented the baking soda from falling out of the balloon into the vinegar containing glass bottle at the time of commencement for the next test. Baking soda was also coated the funnel as it was left wet, following the funnel's use to channel the vinegar into the bottle. Furthermore, it was initially thought that a larger volume of vinegar and baking soda were going to be used. However, we quickly realised that the balloon inflating very quickly made it difficult to measure accurately, so we reduced the quantities of the reactants. We then promptly addressed these issues. To counteract the struggle to get the baking soda out of the wet balloon, an identical but new balloon was used for every trial to ensure the inside was dry. Because the same funnel was used for 2 different purposes, it was exposed to both baking soda powder and vinegar. A towel was added to dry the inside of the funnel after every trial, so that there would be no moisture when it came to use the funnel to channel. By reducing the volume of the reactants, the reaction did not produce carbon dioxide as quickly, therefore slowing the inflation of the balloon. This means that the time taken to inflate the balloon could be measured more accurately. The slower inflation of the balloon was easier to observe and therefore measure. By implementing a number of strategies, we were able to make sure our data was collected accurately. Firstly, through conducting many preliminary trials, using the stopwatch to time the balloon inflation became easier to perform and with less variability. The thermometer accurately measured the water temperature, and 10 minutes was allowed for each test, so the vinegar reached thermal equilibrium. The volumes of the reactants were accurately measured using a cup as scoop. The funnel then ensured that minimal reactant was lost when changing vessels. The baking soda was well separated from the vinegar inside a completely deflated balloon, but then was quickly added to the vinegar in a closed system to contain all carbon dioxide gas produced, as that was what we were measuring, in essence. The endpoint was then easily observed when the balloon was inflated to the upright position without any surface creases. This is approximately 90 centimetres cubed. A stopwatch with multiple trials for each vinegar temperature accurately timed the reaction, and the average times were calculated. Our data clearly demonstrated that as the temperature of the reactant vinegar decreased, the reaction rate also decreased. This was measured by an increase in the time taken to fill the balloon with 90 centimetres cubed of carbon dioxide gas. This trend appeared to be non-linear as reaction times increased by greater amounts for each 10 degrees Celsius reduction in vinegar temperature. The average reaction time for vinegar at 40 degrees Celsius was 1.03 seconds, which increased to 2.11 seconds at 20 degrees Celsius, and then out to 7.59 seconds at 0 degrees Celsius. The rate of chemical reaction can be changed by altering reactant surface area, pressure, temperature, concentration, or by adding a catalyst. The collision theory states that for a reaction to occur, particles must be able to collide with each other with correct orientation and sufficient energy. Increasing surface area, pressure, and concentration all increase the number of collisions, whilst increasing temperature also increases the particle kinetic energy. This increased kinetic energy means reactants reach the required activation energy level more quickly, in doing so, increasing reaction rate. This experiment supports the scientific theory, as the reaction rate repeatedly increases with the trials of increasing vinegar temperature. At higher temperatures, the vinegar particles will be colliding with baking soda particles more frequently, and with the increased kinetic energy means they'll more easily reach the activation energy level required. Both the tabulated and graph data did not demonstrate any outlier results. This may be explained by the extensive preliminary trials being conducted to rectify any problems before recorded tests were taken. Examples include leaving the vinegar in the bottle for 10 minutes to reach thermal equilibrium with the water temperature before each test, refining the method to keep the baking soda in the deflated balloon separate from the vinegar in the bottle but still in a closed system, and being able to mix these two reactants quickly at the commencement of timing produce more accurate results. Also, using the easily identified endpoint of the balloon being sufficiently inflated to stand upright with no surface creases increase the accuracy. Despite no outlier data points, possible solutions of error in results still may have occurred. The reaction times recorded, particularly at higher vinegar temperatures, became quite short. For example, when vinegar was heated to 40 degrees Celsius, the reaction time was only 1.03 seconds. This short time became more difficult to measure accurately, as it required judgment to start and stop a stopwatch with little reaction time between. If a larger balloon was used, and reaction times were increased, then it may have been able to be timed with even greater accuracy. In summary, the hypothesis is supported that if the temperature of the vinegar is increased to 40 degrees Celsius, then the rate of reaction will also increase.